시작할까요? 안녕하세요. Hi, everybody. Let's get started. All right. So, thanks a lot for the opportunity of being here. It's going to be in English, my talk. Just the intro in Korean. Thanks a lot for the opportunity for being here and being able to share with you some of my work and some of my ideas. My name is Andrea. I'm a professor in industrial design, and I'm also a joint professor in the School of Computing. My background is in CS, in robotics, and I was a professor in computer science in Songjinguang University before coming over here. And here in KAIST I have a lab called the Make Interact Lab. We'll see a little bit later. So what today I'm going to do is I'm going to share some very, very opinionated ideas, which maybe you don't agree with, but it's going to be food for thought, okay? So I'm going to try to provoke you a little bit. And I'm going to make it very theatrical. So I'm going to have 3 acts. First act, the end of programming. So when I was asked to give a talk here for the class CS for All, I thought immediately one of the things that a professor in NYU, when I was a grad student, told me, that is computer science is actually a very funny name. Because it's not about computers. It's not a science. It's not a science because, it is skipping. It's not a science because it does not follow any scientific method. There is not an empirical exploration of reality. There are no experiments. It's not a science. And it's not about computers. At least it's not about computers as we intend them today, as electronic devices. Now, if you think about computers in a very general and abstract way, including people in the 40s being computers, that was a job, then yeah, we can say that we are talking about computers. But as of 2023, we don't do this stuff, right? We don't do hardware. We don't really care about buses, capacitance, voltage level that happen on your motherboard. We really don't care. It's not about computer. So what is about? So, in the struggle to understand what computer science is about, many departments try to rebrand themselves as computer engineering, and perhaps that to attract more engineering students. In my school, when I was in NYU, now they have 2 computer science departments. So I graduated from computer science in a mathematical science institute, but now they also have computer engineering. If you notice, UNIST, Solder, they all have computer engineering and science, computer science and engineering. I kind of prefer what KAIST went for, like this idea of informatics or school of computing. And I would argue it's not just about the name. Computing is actually a very good word, and it's more really than the name itself. Because it kind of shifts our attention, our focus from computers to the activity of computing or the result of computing. It shifts our attention from computers to computing, right? From the instruments to the music. That's all. That's all the idea. And if you like this analogy here about thinking computing in this way, well, then maybe you agree with me that perhaps there is not really much music unless you play an instrument, in the same way as there is no computing unless you do some programming. Now, I would argue that music is beyond playing instrument, as computing is more than just programming. But you probably would agree that programming is a big chunk of that idea of computing. It's very important. I would like to say that it's fundamental to computing, the ability of being able to program, at least for 2 reasons. One is because programming shapes the way we think. Right? It's not about the language you use, it's how we think. Steve Jobs used to say, everybody here should learn how to do programming because it teaches you how to think. So that's one key point. And the second reason, programming is just a very powerful tool that takes an abstract idea and boom, you make a product. You make something very, very concrete. And that very concrete is very desired in the market. And if you look at jobs, most of people that study here computer science, they will end up becoming developers of some sort. So programming is also very much appreciated in the market. Except that programming is dead. Programming is over. This article here came out a couple of months ago. It's a little bit of a provocation, written by Matt Welch, the CEO of Fix AI. And what he's saying is that even if we don't notice it, we're dinosaurs, and the meteor is striking. Because programming, as we know today, and as we teach it today, is done. Let me summarize this article for you. He came up with 3 key concepts. Concept number 1, the developer as a job, as a profession, is over. There's not going to be any money in that. In the same way as foam modeler don't exist anymore. What's a foam modeler? Any product like this one used to be handcrafted with foam before production. That's gone. People use CAD and 3D printing. Ham radio operators. Well, they still exist as a hobby, but you're not going to call your girlfriend or so on ham radio. You're just going to use your phone and 5G. That job is gone. Car mechanics, 2035. EU said no more combustion engine. Car mechanics are gone. We are going to have electrical vehicle. And programmers in this list. That does not mean that programmer is going to disappear completely. There's not going to be enough of it. There's just going to be not much money in that particular business. Instead, programmer will become something like a product manager. Somebody that speaks many languages. It does a little bit of tech, does a little bit of business, does a little bit of UX, and orchestrate all these tools, most of them powered by AI, to produce something. So the developer of the future is not going to be somebody writing code. That's key point number 1. Number 2, computer science department will have to think very carefully how to evolve. We teach, and I was teaching these classes too. I was teaching algorithms, data structure, operating system compilers. Those are the basic of our computer science foundation. And are practically becoming very quickly irrelevant. When a computer software is going to be able to write program, you don't really care about how to optimize your quicksort, because it's going to do it. So we used to have tools that we used to teach in school. Punch cards to write code. A slide ruler in electronics, resistor code. But who does use them today, right? When most of your electronics, it's at almost microscopic level, actual resistors with code in colors is just in the realm of hobby and maybe schools. That's all gone. So computer science department will have to really rethink about what is core about computing and to teach. And the third point, most of you might say, well, AI is coming. I would be an AI engineer and making models. But unfortunately, that also is gone. Now we have a lot of people, a lot of companies making models. It looks very exciting. And that reminds me when I was a kid. And we had so many search engines. There's so many. And today, when we look search engine, it's basically an consolidated oligopoly. You only have 1 or 2, right? Those are the one that matters. So large language model probably will end up being just few of them. You don't have to take my word for that. This guy here, Kai-Fu Lee, Google former president, Google China former president. He wrote very clearly in his book, models don't matter in the long run. What it matters is data and what you do with it. The models are going to be given. It's like operating systems. We don't make operating systems. We just use Windows, Mac, and Linux. That's it. We are not going to make them new. But in the 80s, there was so many of those, right? So also machine learning models. We are not going to have many. And if you are planning a career as an AI engineer, you might have to think a little bit. So the job of the developer, the programmer, the person that in the quiet of his room type code, it's actually gone. The fun probably will no longer really exist. Now, obviously, this is not going to happen really quickly, but it's going to happen quicker than you think. Here what is going to happen. Now, you write your code, and some productivity tool like Copilot help you. And that's a boost on your productivity. Not far away from now, you will write the test, and Copilot will write the code. You will only write the test, and make sure the Copilot doesn't screw it up. And then finally, you will give a large specification kind of provide quality control, but the code is going to be pretty much generated automatically for you. And that's probably what is going to happen. And we're here. That's us now. Let me drink some water. Hold on. So, we're here, the end of programming. So get to the second part of my, I think it's going to be a short talk, so don't worry, you don't have to stay here 1 hour. But my view of some opportunities that we still have over there. And I call this my second act, when code becomes physical. Let's shift gear for 1 second and stop talking about artificial intelligence, and let's talk about human intelligence. Now, I'm not a psychologist, so I'm not going to try to argue where intelligence comes from. But I really like this quote. This quote from Maria Montessori. If you don't know Montessori, Maria Montessori was an educator in the 19th century, and she came up with many of the ideas that then formed our education system of using a lot of physical interaction for teaching. So the quote is, "The hands are the instruments of man's intelligence." And why I like this is because I can see two things in this. The first one is that hands are physical and somehow represent the embodiment of our intelligence. And what I mean with embodiment of our intelligence? Our intelligence is not abstract. Think about your hands. We use hand reason in base 10 simply because Mother Nature made us with 10 fingers. Our number system, our unit of metric system, they're all based on base 10 for pure chance. So the fact that physically we counted with 10 fingers impacted so much in the history of how we evolved and how the way we were thinking about computing in the early stages, in calculation, and so on. The second thing is that you use the word instrument. And I like this idea that we can use our body, but also other things to really augment what we can do. So our intelligence is not something only abstract. Think about the writing system. Think about the fact that we can write something down. Simply the fact that we can write down numbers immensely increase our memory, immensely increase our capability to multiply numbers. Simply the fact of being able to write in them. The physicality of this is very important, and that is the key aspect over here. It's so important that maybe you recognize this. This is Stanley Kubrick, 2001 Odyssey in the Space. And it's the moment in which Stanley Kubrick envisioned the birth of human. From apes to human being. The moment that we differentiate from animal is when the ape took a bone and used it as a tool. And that is the moment of the dawn of humanity, when we started up. We start using tool to empower our body and to empower our intelligence. Computer in some ways is a tool like that. So empowering a tool in our bodies, of course, grew much more than using stick and bones. We empower our locomotion, our strength, our vision, and our ability to explore the world using tools that are physical and are fundamental for us. So my vision is that while software and AI, the artificial intelligence, are on this side, on the other side we have physical tools. It's the physical intelligence that we have as a human being. And there is this tension between the two. But where the intersection happens, something magic happens. And that magic is when our code can become physical. And then we have a say over AI. What do I mean we have a say over AI? Elon Musk. Elon Musk was simply saying, oh, we keep delaying our self-driving car. It will happen. The reason why we delay is difficult because it's a real world that AI has to solve. And there is nothing that has more degree of freedom than reality. So somehow the limitation of AI, it's that physical part, which is the opposite for us. The physical part is the part where we actually flourish as human beings. And that's why I had this yin and yang, right? So where the code becomes physical. So in my lab, what we do is that. What we do is computationally augmented physical interaction. And we do that by building tools. So now I'm going to show you some of these tools, very quickly discuss them, and probably in 15 minutes we're going to be done. So, again, this picture here, I like to use it as a framework to kind of show you some stuff. I'm going to show you now some tools that augment us, that make us stronger, that give us more capabilities. But these tools also change our perception of reality. They alter the way in which we see the world. Okay? So under this construction, I'm going to show you two groups of projects. Some of them, I call them computational tools that shape our perception, and other one a computational tool that enable us for building things. Let's start from the first one. So this one here, let's see if you start the video. This is a simple project we did. It took a lot of time. It's a virtual reality application. What we have, it's a 3D world made with a pin array. So you walk on it, and this is shaped. And of course, it's shaped mechanically, right? So you could have this is an interactive game. You can see what is actually happening, right? So when you throw a rock, then eventually the rock appears, and you can cross across the Grand Canyon. It's speed up, but this is actually what is actually happening, right? And just want to show you the way it works is this. If you are curious, it's not a fake. What it is we have a shape generator, which is basically this big machine that go underneath. And then we have motors in a modular style system that we push this array of pins and push and pull using electromagnets on the top. So we can create all kind of shapes. It's a little bit slow, but a big technical innovation, you can walk on it. That has never been done before. My students had to assemble a few thousand pieces of wood and 15,000 magnets. That was a nightmare. All right, here another project. This one, we did it with Microsoft Research. And the idea is we have two haptic controllers in your hand. And what they do is they move independently. But when you are in VR, you think they are connected. So they move in this way. They can rotate, bend, stretch. But when you move them together, it creates the illusion that you have something in your hand that is moving, like a rope. Okay, so I accelerate the video to save a little bit of time. Here you can see breaking objects, and you feel the snapping inside of your hand. Even if they're not connected, it gives you that illusion. You think they are connected. You feel the weight of the fish from one side to the other side, very realistically. And you can also build the tools that constrain to each other. So you really feel you have in your hand something physical that does not deform. So these are all examples of what is possible by building novel controllers. One last one. This is really recent work. We are going to present it in April at KAI, still with Microsoft Research. And what it is the idea that we can do yoga, but augment that yoga. And what we did is augmented reality representation. So instead of seeing a video on a screen, you see a video in your augmented reality glasses. And regardless how you move, that can follow you, or might follow the instruction, or could be surrounding you. So this, for example, the blue one is the instructor, the original instructor motion capture that we did using both a motion capture suit and also using what is called pose estimation. It's a Google Blaze algorithm. Then we test this stuff. We tested in labs, and then we tested at home, and we found how people actually do interact with yoga in a much better way than not looking on a fixed screen like a TV or an iPad. Okay? So these were 3 projects of what I call computing tools that alter your perception of reality. Now I want to show you 3 other small projects that what they do are tools that enable you to build stuff. The first one, it's an electronic prototyping toolkit. Let's see if you start. Okay. So you might be familiar with the word physical computing, Arduino projects, stuff like that. So what we have here, it's a breadboard where you can build a circuit. But the difference is that you place components on the breadboard, but you don't wire it. You wire in software, and yet it works. How does it do that? It makes the wiring for you, underneath. They're invisible. So here you have a circuit, and you can see there are no wires, and it's still working. You can test different RC filters configuration without putting any wire physically, but just virtually in your software. And that will update automatically for you the circuit. It's kind of like the idea of FPGA, but at macro level. Here you change it from I2T to SPI by rerouting completely. And here, I don't have the music on this one, but actually, it plays some music and the LED blink accordingly. And this is an example of some kind of analog circuit you can do. And what the system also does for you is that you can just create your schematics and it guides you on how to place the components. So you made your schematics, it guides you, and eventually when you're happy, you can even print it or mill it, take your board, put it on your Arduino, go to your circuit that has no wire, take it off, plug it in, all works. This one is another example of electronics, where in this case, you are the PCB. You are the electronic part. We print on the body. So we have a mini plotter. And what we do is we inject conductive ink. And we use this one for fabricating, in this case, a sensor. So we have a sensor here. Doesn't look like a sensor, but a straight gauge sensor. You apply a little bit of isolator, insulant, just to help a little bit, and then plug it in, perform a minimal calibration, or even draw anything by hand you want on the top of that. You perform a kind of calibration because, of course, your body is now flat. And once you did that, and let's give it a second for doing that. It looks scary, eh? But it's not. You perform your calibration, and then go and print it. And all the process will take about 5 minutes. And you print your circuit directly on the skin. And when you're done with that, you can even plug in the still wet conductive ink, tiny resistor over there, made a voltage divider. And now what I have, well, every time you bend, stretch, or anything, I can sense it. Very, very easy. Here I'm just simply stretching the skin. Here I'm touching other people, and I can tell somebody's touching. Yep. And you can tell from the capacitance. You can tell if you are taking steps, if you're walking, if you're running, if you're jumping. You can also do a little bit of art. This is an LED that is turning on, and then we put these kind of things everywhere. I don't have pictures here, but we print it on the head, on the on the neck, on the arms, in all different parts of the body to demonstrate that. One last project. This project here is called Shrink Cell, and it's the idea of having 3D printed objects that when you just print them, they can move without any motor or anything like that. So what we have here, it's objects that are just 3D printed and they move. And we can control how they move, how fast, how much. And the way it works is because we use the residual stress of this polymer. And by basically constructing computationally a kind of geometry internally, we can choose how to bend them and which one to hit so that we release that stress and cause the actuation. So this is a computational tool we built, and these are examples of moving objects, objects with electronics, like a little lamp that is moving. Or here we have a phone holder, and we can choose not to have collision. One part is moving first, and only after a while, the other part will move. So it's kind of 4D printing, but with no collision, which is pretty new. And then you have your beautiful phone holder for your phone. And that was Shirin Cell. Right. So what did I show you? I said before what we do, and what I wanted to show you is how the code becomes physical. What we do is computationally augmenting the reality. Computationally augmenting our interaction with the reality, the physical interaction. And we do that in two ways. In one way, we augment your perception of that reality by using VR or augmented reality and alter that perception. And in another case, what we do is we use material. And when I say material, I mean physical material, including your body, to build tools that have some computational capability built into the object itself. The object becomes computational. Act 3. This is going to be very short. I drink 1 second. Sorry. So, I come from design, so I'm a little bit biased toward this, but I want to leave a message at the end. We started by saying, programming, as we know it today, it's over. And if you're really thinking to do a career in development, you should really think it carefully, honestly. But there are other avenues that we have in front of us. Now, I can't really tell you if the future is going to be a sad future, where we are no longer needed, or a happy future. This is, by the way, a very interesting article from the guy that actually made VI, one of the most famous editors. I'm sure you know it. It's Billy Joy. Very negative view of the world, but I don't know which one is actually going to happen. But I know for sure, that the developer, as we think it today, a very specialistic profession, the programmer, that will no longer exist. What we're going to have is generalists, product managers, people that are capable of orchestrating lots of tools. And how I call that? I call them a designer. Now you might feel like, why is a designer that? Isn't design about drawing? Right? Design in Italian, disegno, they're very similar. It's about drawing. And I always struggle with that, including in my own department. Design has absolutely nothing to do with drawing. Design comes from a Latin word, actually. That means designum. That means to choose. To choose is exactly what I was describing to you 5 seconds ago. The job of a person capable of orchestrating stuff, capable of making high-level decisions involving software, hardware, materials, and put them all together to make your product. That is the designer, not the guy that is drawing. Okay? And what I think is AI will only enhance this profession. And what I think is the designer of the future will be able to bridge computing with the physical world to build a new renaissance. We build in our lab the future of computing. Come and join us if you care about it. Thank you. My last, it's me. If there is any question, I'll take it. I'll be happy to take it. But otherwise, you gain 30 minutes free. 수기님 어떻게 할 거야? 끝났어요? 어떻게 해요?
혹시 질문 있으시면 교수님께 영어로 하시면 더 좋을 것 같고 한국어로 하셔도 좋을 것 같습니다. 네.
말하면 되네요. 강의 잘 들었습니다. 우선은 많은 어떤 되게 신기한 걸 보여주셨는데 그런 거를 함에 있어서 어떤 하드웨어적인 뒷받침이 필요한데 그게 현재 교수님이 저걸 만드시면서 생각하시기에 좀 더 하드웨어적인 발전이 필요하다고 보시는지 아니면 지금쯤이면 지금 있는 걸로 충분하다고 생각하시는지 그런 거 좀 궁금합니다.
Okay. Let me rephrase it and say in English also for the audience. So if I well understood, you're asking me whether the level of current existing hardware is enough to envision this world. Is that correct? So I think it's always a matter of pushing the bar. The current hardware, it's evolving really, really rapidly. Materials are crazy. It's so much innovation in materials. So specifically in my field, human-computer interaction, I like to go and bridge between things. So oftentimes we go to material scientists and try to talk with them. I don't think it's enough what we have now, but I think it provides a very good base to start. A lot of the things are actually, that can be done, are a little bit low-hanging fruit. There is a lot of stuff out there that surprisingly has not been done yet. The way we conceive the physical world and the way we conceive software is so distinct that there are so many opportunities to bridge them and bring them together. I can't come up really with a single example, but I feel like IoT perhaps is something that comes to mind of that attempt to bridge the physical world with the virtual world, but it's really, really at the early stages. And I think there is much, much more, at least in research and so on. I hope you answer, otherwise afterwards I can talk more.
혹시 봤던 기술들 중에 지금 혹시 그 상업화가 되거나 커머셜라이즈 되거나 아니면 현재 사회에서 실제로 사용하고 있는 기술들이 몇 개가 있을까요?
Let me recap and let's see if I got it right. So you're saying of the stuff that I've been showing, their practicality in the industry or commercially viability, does it exist? How many of these are real products? So to be honest, many of the things I do are almost intentionally not real product. And the reason is because if you try to do a real product, that's enough of a research. So I feel like my job as being a researcher is try to envision a path, and therefore what I do, I can't say immediately it could become a product. However, what we learn by doing that kind of research many times can be directly applicable. I'll give you just one quick example. We made one haptic controller last year, still with Microsoft, and it's gigantic. So it's totally not realistic to sell that. It's a gigantic haptic controller. But what we learned is that when we did it, the effect that we wanted to create, the illusion that we wanted to create can be delivered with a very, 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 very simplified version of that, which we then developed. And therefore, that could be included, say, in your next joystick or controller for your PlayStation or something like that. So by doing research and maybe doing something that is completely absurd, we learn something that is viable. Some other things, like the yoga one, I think can become a product. But say the terrain with the pin, yeah, that is a little bit not really a product yet. So I hope I answered. If there are questions, my door is always open. And so don't feel the pressure to ask here. And I'm also can stay here a little bit longer. What about I let everybody go? Have a good week.
네.